Good morning. Good morning, dear student. Good morning to all.
Good morning, sir.
So let us start our session. This is the fourth class of MCS 230. In the last class, we have discussed some important transform techniques. One is DFT and another is DCT. Please recall the discrete Fourier transform is used to image processing to transform an image from its spatial domain to the frequency domain, revealing its frequency content. So the frequency content will not change, the content will be not changed. Only this transform is used to convert an image from one platform, from one domain to another domain. Here from spatial domain to the frequency domain. So once it is converted to frequency domain, you perform some operation like or smoothing, enhancement, sharpening. Then it is converted to its original spatial domain by using inverse discrete Fourier transform IDFT. This allows obvious your video is on. This allow for tasks such as image filtering, compression, and enhancement by manipulating the frequency component. So once it is converted to frequency domain, so now you can make such type of operation, image filtering, image compression, and enhancement, which correspond to different type of image feature like edge, high frequency, or smooth areas, low frequency. Uh, so we have discussed it, and these are some application: image uh, filtering, and once it is converted to spatial domain to frequency domain, you perform such type of applications operations. So after completing the operation, it need to be converted to its original domain, that is the spatial domain, which is achieved by applying IDFT, inverse discrete Fourier transform. As the name suggests, inverse discrete Fourier transform, it converts the transformed form image which was in frequency domain to the spatial domain, which is the original domain. So the inverse discrete Fourier transform construct an original image from its DFT, which represent the image in the frequency domain. So you know that in DFT the image is in frequency domain, so it need to be transformed to the spatial domain as its original domain. By applying IDFT to the frequency domain data, which consists of both magnitude and phase information, the IDFT converts it back to the partial domain, yielding the original image pixel. Okay, the original pixel will not change. The process is crucial for image filtering and restoration after manipulate are formed by the frequency. So here the image filtering and restoration के लिए क्या यूज होता है DFT. So you see what type of operation DFT supports. So once it converted to the frequency domain, one an image which initially was in spatial domain, now it is converted to frequency domain. You can perform this type of operation. So in the frequency domain, we can modify the image by filtering it. We can apply different type of filtering methods, filtering techniques. So for example, we can remove noise, different type of noise from the image. Besides that, we can edge sharpening uh, uh, that image. We can also besides these two operation, we can also reconstruct it. The inverse IDFT is then applied to the modified frequency domain data to reconstruct the image to get the data back in its original form. separable property. As you know, the 2D identity is separable. One first, that is one D IDFT is used for each row in the image, followed by another ID one dimensional IDFT on each column of the resulting image. So that is why it is called separable. So the second technique, which is the DCT, a technique that convert an image spatial domain data into frequency component. The same function as the previous one, but here you can compress the image. You can compress the image. In previous case, we can only remove the noise, reconstruction, some sharpening, and it is separable. But once the image is converted using DCT, you can apply the special type of operation, image compression. You can compress the image. If its size is more, you can compress it to a smaller size. It separates an image into combination of cosine waves at different frequency, concentrating the most important visual information, low frequency component, into a few coefficient and making it efficient for lossy information algorithm like JPG, which discarded less important high frequency coefficient. So basically, this is used for image compression. You see, the main application is image compression and filtering. So the most common application as seen in JPG format show reducing the size of the image. Once the size is reduced, will take less space to store. Besides that, it also you can send the data or send the compressed picture or compressed image to other destination which moves fast as the size is reduced. Besides that, DCT can also be used on image filtering by performing symmetric convolution, a different form of convolution that is more efficient in frequency domain. So many times it is asked that what is the difference between DFT versus DCT? It is a common question, uh, and you see, let us find what is the difference. The main difference is that the discrete cosine transform is preferred for image compression. As you know, if your aim is to compress the image, so you prefer DCT to DFT. So it is preferred for image compression like JPG because it compact energy more efficient into fewer coefficient and produce only real values, where the DFT use both sine and cosine result in complex values and is less suitable for compression. So as compared to DCT, DFT is less suitable for compression because it is contains the both sine and cosine waves, but DCT only use the cosine waves. DFT is more general and widely used for spectral analysis, that is DCT used for cosine functions and specific boundary condition, make it more efficient for lossy compression and algorithm. If the compression image compression के लिए DCT use होता है, the DCT is more preferred than DFT if your aim is to compress the image. Besides that, the image transforms are needed to simplify complex problem, extract specific features, and make image more suitable for storage, transmission, and further analysis. This is the need of image transformation. So, by converting an image from original domain to another, that is the spatial domain to like frequency domain, transform can reveal hidden information, isolate important component, and improve efficiency. So that you can perform some operation suitably. Common application include image compression, edge detection, and image enhancement once the image is transformed to spatial domain to frequency domain. So you can perform such type of operation. In frequency domain, it is easier. Feature extraction. Transform can highlight features that are not obvious in the spatial domain, such as edge and pattern. So some features are not uh, obvious or not suitable in spatial domain. So that is why we need to convert the image from spatial domain to frequency domain. You see, technique like DST can represent an image more compactly, reducing file size for more efficient storage and transmission. So that is why we know that DCT is used for file compression, enhancement and restoration. Transformation allow for improving image quality by separating noise from relevant information. You know that transformation after transformation it is easy to remove the noise. So you will get a better quality uh, of an image. So adjusting brightness and sharpening details. So you will get a better quality image. That is why we need transform. And the third application is third cause is geometric manipulation. Basic transformation are used to change an image spatial arrangement, which is essential for taxal and resizing and rotation. Suppose you want to rotate an image by 90 degree, by 60 degree. Suppose you want to change the size of the image, shape of the image. So this is the geometric manipulation becomes easy. You can perform this manipulation easily once it is converted to uh, frequency domain. Simplified analysis. By changing the image representation, transforms can make complex tasks like pattern recognition and convolution easier to perform. Alternate representation. Transform provide a different perspective on the image data that may be more useful for specific applications such as in medical image or remote sensing. So for some application, the transform data is more useful, like your medical imaging or remote sensing. So that is why we need transform. So these are the need of transform. So you may ask, may ask a question. What are the need of the transform? Why do you transform in an image from one domain to another domain? So these are the reasons why we need transformation. Let us see some important questions, some numerical questions. I have collected this question from the previous year questions. Given a grayscale image with aspect ratio 6:2 and pixel resolution of uh, 4,80,000 pixel, calculate the dimension of image, size of the image. Okay, so this is a question which is given, aspect ratio is given and resolution also given. Now, the question is find the dimension of the image and size of the image. You see here. Let us start from calculate the image dimension, which is given in the question. The aspect ratio means width proportional to height. That is, which is to height is 6:2. It is given in the question. Which simplified 3:1. 3:2 means the same as 3:1. Let the height be h and the width be w, such that w equal to 3h. Because we know that the width height ratio is 3:1. So width by height equal to 3/1. So if we cross multiply, we get w is equal to 3h. That is, w is 3 times greater than h. The total pixel resolution is the product of width and height. That is, w into h is equal to this value, 4,08,000. So as you know, w is 3 times greater than h. So we can put 3h in place of w. That is 3h into h. That is your 4,08,000 and 3h square. This, so h square is equal to 1,06,000 and h is root over that amount is 400 pixel and width is 1200 pixel. So this is the dimension it is given. So the question is easy, but you see this is the aspect ratio, that is W by height. So now we can able to find the W and H, where H is 400 and width is 1200. If you see, if we multiply these two, we will get the resolution 4,80,000. 400 into 1200. So now we are able to find W and H. Are you getting? Then there was an additional question. Calculate the image size. Standard grayscale image use 8 bit. We know there is a maximum 250 possible values. The total size in bytes is the total number of pixel multiplied by the bytes per pixel. So size is equal to total pixel per bytes per pixel. So as it is 8 bit, a gray level scale image is 8 bit, so it is 1 byte. And the size is total pixel into bytes per pixel, not bits. If you multiply 8, you will get wrong answer. So byte per pixel. If it is 8 bits, so you can put that convert to that 2 bytes. So we know that 8 bits is equivalent to 1 bytes. So your 4,08,000 into 1 byte, so 4,08,000 bytes. So you see this pixel bytes per pixel will cancel, so you will get bytes. So this is the size of the image. So image size is 4,08,000 bytes and image dimension was 400 into 1200 pixel. So the final answer is the dimensions of the image are 1200 pixel by 400 pixel or 1200 into 400 pixels. The resolution of the image is, sorry, the size of the image is 4,08,000 bytes or approximately 468.75 kilobytes. If we divide it by, it is 1024 bytes, so you will get 468.75 kilobyte. So this is a simple question. This question came in the last question. I have collected this question from the previous year's questions. So this is not difficult at all, but there are simple formula. So how the size is calculated here, total pixel into byte per pixels. In previous one, it is a that is your W into H, and the aspect ratio is defined at width by height. Width, if you take the ratio of width to height, this is known as the aspect ratio. You should know these terms. Otherwise, this is difficult for you to solve. Come to the second question. For a sample mobile phone with height and width resolution is 1080 into 1920 pixel. Okay, this is the height and the width resolution of a sample mobile phone. And the diagonal size is 5.0 inch. Your phone diagonal size is 5 inch. We know that we have the diagonal mobile size is 5 inch, 5.5, 6 inch. So calculate pixel density in pixel per inch. We have to calculate the pixel density per inch. Per inch means that is from a square inch. So we have to remember some formula. Calculate the diagonal resolution of the pixel. And first determine the screen's diagonal resolution in pixel using the Pythagorean theorem, where W is equal to width, height, and height. Where W is the width and H is the height. So as we know, if the diagonal, so it is form a uh, uh, triangle. The triangle, one side is 90. Suppose you see your screen, the one side is 90. If you draw the diagonal, you will get a triangle which 1 degree is 90 degree. So you can use your Pythagoras theorem, where h square equal to p square plus b square. So so d pixel equal to, you see, w square plus h square width and height root over. So you find the d pixel, that is the you will find the h here. You see 1080 square plus 1920 square root over. It is calculated, and the summation is this, and you will get root over the amount calculated there, and finally we will get it approximately 2202.91 pixels. So once it is calculated, it is easy for calculate the pixel density, which is shortly known as PPI, pixel density per inch. So next, divide the diagonal resolution in pixel by the physical diagonal size in inches, D, to find the pixel density, PPI, which is calculated by D pixel divided by D. What is D? That is the physical diagonal size, which is given in the question. That is 5.0. You see, in the previous question given into 5 inch. You see, and the diagonal size of 5 inch. So D is given is 5 inch. So that is why I am dividing that value, D pixel value, by 5, and it is calculated as 440.58 ppm. So this question is also not difficult, but you should know this formula to find out this. So as it is, it form a right angle triangle. Your screen, your width, height, and diagonal form a right angle triangle. So as it is form a right angle triangle, we can use Pythagoras theorem to find the d pixel value, which is divided by the physical diagonal size, d, in inch. But sometimes the diagonal size is given in feet. So you have to convert that. If it's given in other unit, you have to convert that to the inch. So here the size is given 5 inch, so we don't have any problem here. But if it is given in other unit, you have to convert the to the inch. So here 440 point something is the answer. This is the pixel density, PPI. So I saw some questions will uh, this type: compute the discrete constant transform discrete matrix for order 2. How to compute this, a discrete constant discrete matrix for order 2? The discrete constant transform DCT has several variants. Okay, type 1 to type 4. with DCT2 being the most common, notably using the JPG compression. We know that the JPG, the DCT is used for compress a file. So it is used for JPG compression. The formula provided below is for the orthogonal DCT2 matrix of order n. The DCT matrix of order n, so n equal to 2 here, is computed using the formula for its element ckn. You see, ckn equal to alpha k cos pi 2n plus 1k by 2n. It seems difficult, it seems complex, but actually it is easy. N is the order of the matrix. Here is it 2. N is the row index starting from 0 to n minus 1. If it is order 2, so starting from 0 to 1. K is the column index. Here is also n is equal to 2. So it is 0 to n, that is 0 to 1. So row n is 0 to 1, k is 0 to 1. Alpha k is the normalized factor which is calculated by 1 by root n. So here alpha k is equal to 2 to power root n for k greater than 0. So the alpha k is calculated alpha 0. The first value is where k is equal to 0, it is alpha by root n. Where alpha for alpha k, it is 2 to power root n, where k greater than 0. So alpha I value has two formula. One is 1 by root n if k is 0. If k is greater than 0, that is k1 or k2, we will get another formula. It is root over of 2 to power root n, 2 by root n. So let us take an example to calculate this. This is not difficult at all. So some value is missing, I think. So calculate the normalized factor first. Alpha 0, 1 by root n, 1 by root 2. Alpha 1 here is 2 by root over of 2 by n. So root over 2, because here the value of k is greater than 0. So that is why we apply different formula. 2 by 2, root over 2 by 2, which gives 1. So we calculate alpha 0 and alpha 1. As it is a 2 cross 2 matrix, so the possible k value is 0, 1. So we calculated alpha 0 and alpha 1. For other values, we can calculate the alpha 1, alpha 2. So here alpha 0, alpha 1, because it is a 2 cross 2 matrix. So we have to go, k values goes from 0 to n minus 1, 0 to 1. So as n is 2 here, so we have to 0, 1, 2 values only. Then calculate each element of the 2 cross 2 matrix. C00. C00 is equal to alpha 0 cos pi 2 into 0 plus 1 into 0 using this formula. You see, alpha kn ckn is equal to C00 equal to alpha k, so value is 0, k value 0 here. So alpha 0 cos pi into 2 into 0 plus 1, k is also 0 by 2n, 2 into 2, 4. You see here. So alpha 0 is equal to cos 1 by root 2. So pi 2 into 0, pi something 0, 0 by, so pi 0. So it is pi. So you see the numerator is multiplied by 0. So the value is 0. So 1 by 2 cos 0. It is not written there. I have to write there 1 by 2 cos 0. So okay, so it is 1, cos 0 is 1. So you see there is a 1 value. Similarly, we go for 0, 1, C01, where k is equal to 0, n equal to 1. Kn. So k is equal to 0, n equal to 1. So alpha 0, alpha k, cos this value pi into 2 into 1. So you will get the same value because 0 is multiplied in the numerator. So 0 by 4, you will get 1 by root 2 cos 0. 0 is not written there. It is not visible. So it is 1 by 2 cos 0 also. So it is 1 by root 2 into cos 0 is 1. So 1 by root 2. So the first 1 and 2 have produced the same result. Then go to the third part, C10. Here k value changes. K is 1, n equal to 0. So alpha 1 here. So alpha 1 is 1, not 1 by root 2. Alpha 1 is 1. You see it is calculated in part 1. So cos 2 into 0 plus 1 into 1 by 2. So it is 1 into cos 2 into 0, 2. That is cos pi by 4, whose value is 1 by root 2. Cos pi by 4, you see. The numerator gives pi 2 into 0, 0 plus 1. That is pi into 1, pi by 4. So cos pi by 4 is 1 by root 2. So it is also gives the value 1 by root 2. 1 into 1 by root 2, 1 by root 2. So the answer of the third one is 1 by root 2. Let us come to the fourth one, last one. C11. Because we have to go to value 0 to 1. As n is equal to 2, you have to go starting from 0 and 1. C11. K1, N1. So C1 is equal to alpha 1 cos pi into 2, 1 pi 1, 2, 2. So your 2 into 1, 3. So pi 3 by 4, which is equal to minus 1 by root 2. So 1 into minus 1 by root 2 is equal to minus 1 by root 2. So the answer of the fourth one is minus 1 by root 2. Are you getting? It is not written. That is the last value is minus 1 by root 2. Because it is cos 3 by 4. Cos 3 by 4 is equal to minus cos pi by 4. So minus cos by pi means cos by pi 4 is 1 by root 2. So it gives minus 1 by root 2. So we got the answer. 1 is 1 by root 2. The second is 1 by root 2. The third is 1 by root 2. And fourth one is minus 1 by root 2. You know it? 1 by root 2, then 1 by root 2, then 1 by root 2, and the last one is minus 1 by root 2. Okay. So let us form a matrix by taking this value C00, C01, C11, C11, C10, C11. So C00 is the first element, 0th row and 0th column, that is first row and first column. C01, C10, C11, you see. So the matrix can also be presented with a common scaling factor pulled out. So there is a 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Taking 1 by root 2 outside of the matrix, so it form 1, 1, 1 minus 1. And more commonly, this matrix is orthonormal. You know that a matrix is said to be orthonormal if its inverse is equal to its transpose. So the cosine matrix, the cosine discrete cosine matrix is orthonormal in nature. Orthonormal in nature, because if we take the inverse of the matrix, it is exactly the same the transpose of the matrix. So the nature of this matrix is orthonormal. Okay, so you often got a question. It is a small question. what is the nature of the matrix formed by DCT? What is the discrete cosine transform matrix? The nature of that matrix is orthonormal, where the inverse is equal to the transpose. Okay. So beside these two transform, another is a hard transform. This is this question also came the question, what is hard transform? Give a suitable example and compute the discrete hash from 2 cross 2 matrix. We have already seen that in previous example we got a DCT matrix, discrete matrix, but here is a hard transform matrix. Let us see what is the this transform. So it is different from Fourier transform and discrete cosine transform. The hard transform is a discrete wavelet transform that decomposes an image into different subbands representing low frequency and high frequency detail information by averaging and differentiating adjacent pixels. So it decomposes the image into different subbands. How the subband is calculated? You take the average value of the low frequency or high frequency value. It is computationally simple and fast method widely used in image processing for application like compression and denoising the separation by analyzing the image details. So like your DCT, it is also used in file compression, image compression, and denoising the separation by analyzing image details. If you want to separate the image by some component, if you are interested some part of the image, not the details, also it is used for that purposes. The process involves repeatedly applying averaging and differentiating operation horizontally and vertically to a 2D image. So it is find the average of the each components, like you see the average is calculated in the mean filter average filter which we discussed yesterday. It is also repeatedly applying the averaging and differentiating operation horizontally and vertically to a 2D image. Computing the discrete hard transform of a 2 cross 2 matrix. The, you see, for a 2 cross 2 matrix n equal to 2 here also, the discrete hard transform use the simplest hard matrix often normalized to be orthonormal. The normalized 2 cross matrix we already H2 is equal to suppose 1 by root 2 1 1 1 minus 1. This is the same as n is equal to 2 orthogonal DCT2 matrix. So this is same as matrix. The first row acts as an averaging function and the second row acts as a differentiating functions. The 2D hard transform of an input matrix X is computed as Y is equal to H2 into H2 transpose, or Y is equal to H2 into H2, since H2T is equal to H2 here. Why? Because H2 transpose is equal to H2, because it is this. Let us compute the hard transform of a generic 2 cross 2 input matrix X equal to A, B, C, D. Suppose we have given a matrix, we have to calculate. This is general form, general matrix, whose element is suppose A, B, C, D. Let us compute for the each element of this 2 cross 2 matrix. For a 2 cross 2 matrix, the discrete Hart transform DHT involves applying the one-dimensional transform first to the row and then to the column of the resulting matrix. So we have already known that that is the it is used for the row and the followed by the columns. Let the input matrix be M, and M is equal to, suppose it is given M11, M12, M21, M22. The normalized 2 cross 2 or matrix which is given in previous example, n is equal to 2 is defined as H is equal to 1 by root 2, 1, 1, 1 minus 1. So this is normalized 2 cross 2 matrix. The 2D Hart transform computed by T equal to H M into H transpose, where H transpose is the transpose matrix of H. So we know that the transpose of matrix is obtained by interchanging rows into column and column into rows. Since H is symmetric, so HT is equal to H. So in place of H, we may write uh, H, because as it is a symmetric matrix, so whose transpose is equal to original matrix. We know that a matrix is said to be symmetric if its transpose is equal to the matrix itself. That is, A is AT, and it is known as antisymmetric if A is equal to minus AT. Okay, so please recall the skew symmetric or skew symmetric. It is not symmetric and skew symmetric. So let us take a good example. Step by step method. Suppose is given M equal to 6248. So where small m1 is 6, m12 is 2, m21 is 4, and m22 is 8. So apply this Hart transform to the rows first. M row transform M into H. So 6 M is equal to 6248 into H is equal to 1 by root 2, 1, 1, 1 minus 1. So 1 by root 2, if we multiply this matrix, you see 6 into 1 plus 2 into 8 into 6 into 1 plus 2 into minus 1. Similarly, the first row and first column of the second, 4 into 1 plus 8 into 1, then 4 into 1 into 8 into minus 1. That is row, you will multiply this row of the first and column of the second. So 6 plus 2, 8. The resultant matrix is 1 by root 2. You see 6 plus 2, 8. Then 6 minus 2, 4. And the second row is 4 plus 8, 12. And 4 minus 8 equal to minus 4. Then apply the Hart transform to the column. Multiply the result by H from the left. That is H into M row transform. That is, we have to find H, M, H. M, H, M, H. So MH we have already calculated, then multiply H to the left. So this is same as HMH. H into M into HT. So as HT is equal to H, so we have to multiply H into M into H. So already MH is calculated in the first step. So we have to only multiply H to the left of the MH. So 1 by root 2. H is given 1, 1, 1 minus 1. And the new one is 1 by root 2, 8, 12, 4 minus 4. So 1 by root 2 into 1 by root 2 form 1 by 2. So 8 into 1 plus 1 into 12. Similarly, 1 into 4, 1 into minus 4, 1 into 8. So 1 into minus 12. So this is minus sign is there. So you will get 1 by 2, 8 plus 12, 20, 4 minus 4, 0. The first row. The second row is 8 minus 12 minus 4, and 4 is uh, it is minus 1 minus 4, 8. 4 plus 4, 8. So 20, 0 minus 4, 8 multiplied by 1 by 2. So if we multiply 1 by 2 each element, we will get the final result. So the final result t equal to 10 into 0, that is 1 by 2 multiplied by 20, it gives 10, then 0, then minus 2, that 4. So the result is the final result. So this is the Hart transform. So this is not also difficult, but you have to know that the Hart transform is calculated by HMH, where H is given. You have to find MH. M is given in the question. So first find MH, then multiplied with H in the left side. So the resulting two-cut matrix T contains the transform coefficient. So this question also collected from the previous question papers. This is also important, and uh, uh, it is not difficult at all. But you should know that the simple formula. Okay, otherwise it is difficult for you. So these are some important questions. Basically comes from the transformation and some analytical questions. So I have solved them. So this is all about the transformation and some questions. Then come to the second part, computer vision. Okay. So it is suppose human vision. In which manner we see an object, that is human vision, that is our vision. But the computer does not have any eye like human. Computer does not have eye to see. So how does the computer recognize this object? How does the computer get information for an image? How it gets information that this is the such type of image is there? Suppose this is the image of a busy street. How does the computer recognize that these are some vehicles? These are the vehicles. These are the humans. These are trees. So this is known as computer vision. That is how, which manner computer sees the image and get the information, extract the information from that image. So in this section, we will learn about this. How does the computer extract information from an image? What is the computer vision on an image? Let us see the uh, definition as usual. Computer vision is a branch of artificial intelligence that enable computers to interpret and extract information from image and video, similar to human perception. Okay. So like a human, how does a computer extract information from an image, interpret and extract information from an image and from a video. We are the humans, we have the eyes, we have the brain, so we can extract information from the image easily. This is a vehicle, this is a tree, this is a object, this is a human. So we know that. But how does the computer know? It involves developing algorithm to process visual data and derive meaningful information insights from it. So why computer vision? High demand in the job market. So essential for careers in AI, machine learning, and data science across industries like healthcare, automotive, and robotics. So this is the first application. Revolution industry. Power advances in self-driving cars, medical diagnostics, agriculture, and manufactured by automatic visual tags. This is automatic. No human is involved in this tags. Solving real-world problem. Enhance public safety, improves medical imaging, and optimizes industrial processes. So have we ever wondered how machine can see and understand the world around them, much like human do? So like human, how does the machine see and learn or understand? This is magic of computer vision, a branch of artificial intelligence that enable computers to interpret and analyze digital image, video, and other visual inputs. So how does the computer interpret it and extract information from that video, from that image using uh, computer vision, known as computer vision, and it is a part of the artificial intelligence. For self-driving cars to healthcare diagnostics, you self-driving car, that is a car is moving without a driver. That is there are self-driving. That is when some obstacle comes, the automatically the brakes is put, so the car stops. And healthcare diagnostic, that is there is automatic stacks which recognize the disease of a patient. So computer vision is a revolutionary industry by allowing machine to recognize the object. It is allowing machine, not the human is employed for that purposes. So the machines are employed to detect this, to recognize the object, track movements, and even make decisions based on the what they see, what they observe. It's no better. Oil and natural gas. The oil and natural gas company produce millions of barrels of oil and billions of cubic feet of gas every day. But for this to happen, first the geologists have to find the feasible location from where oil and gas can be extracted. So the geologists have to find a feasible location from where this natural gas and oil has to be found. To find this location, they have to analyze thousands of different locations using image taken on that spot. So they have to analyze the thousand of different locations. Suppose if geologists had to analyze each image manually, how long would it take to find the best location? So there are thousand of images, 1 lakhs of images. So if it is manual done by the geologist, it take more time, maybe months or even a year. But due to introduction of computer vision, using the period of analyzing can be brought down to a few days or even few hours. So within a few hours, it can be done by using AI or computer vision. The machine will run. The machine will detect that. If the number of photographs or images are more, so it takes more time if it done by manually by the humans. Hiring process. In the HR world, computer vision is changing how candidate gets hired in the interview process. By using computer vision, machine learning, and data science, they are able to quantify soft skill, and conduct early candidate assessment to help large companies shortlist the candidate. So this is you know that is this is you do some soft skill quantity so that you can get a shortlisted candidate. Video surveillance. The concept of video tagging is used to tag videos with keywords based on the object that appear in the each scene. Now, image being that security company who's asking to look for a suspect in a blue van among hours and hours of footage. It had to feed the video to the algorithm. With computer vision, the object recognition, searching through video has become a thing of the past. So, from the video, that is the machine will be recognize the object. Suppose there is suspect person is moving inside a location. So from that video, so it will be recognized by the machine. There is some particular algorithm to detect that. Construction. For example, the electric towers or building which require some degree of maintenance to check the degrees of rust and other structural defect. So know that a tower is a or a high electrical towers or building, it needs some maintenance time to time. So we have to check the degrees of rust or other structural defect in it. Certainly, manually climbing up the tower to look at every inch and every corner would be extremely time consuming. So if we take done it manually, it takes uh, more time. Besides that, it is more costly and dangerous. Imagine that if a person on the ground took high resolution image from different angles, then the computer vision specialist would create a custom classifier and use it to detect the flows and amount of rust cracks present. So a high resolution by using a high resolution camera, the good quality picture will be taken, and then it is the computer vision specialist to create a custom classifier and use that image to detect the flows and amount of rust and other defects present in that high tower. So this is also used in construction. The healthcare. From the past few years, the healthcare industry has adopted many next generation technologies that includes AI and machine learning concept. One of them is computer vision, which helps determine or diagnose disease in human or any living creatures. So from the image, the computer vision specialist will find that to detect the disease in a patient, in a patient body. So as the application is large, application is more. This is also used in agriculture. In agriculture, farm have started using computer vision technology in various forms such as smart tractor, smart farming equipment, and drones to help monitor or maintain the field efficiently and easily. It is also help improve yield and quality of crops. Smart tractors, smart farming equipment. So nowadays the modern technology, using the modern technology, so different type of agricultural powering device is used. So the drones also to help the monitor maintain the fields efficiently and easily. So if the area of a land is very large, so monitoring all part of the field is not easy. It is difficult and time consuming, costly. So that is why this helps improve the yield and quality of the crops. Military. In the application of military, in modern armies, computer vision is an important technology that helps them to detect any enemy troops, and it also enhance the targeting capability of guided missile system. So in guided missile system, and if any enemy troop in the area, so it detect that area using the computer vision. It uses image sensor to deliver battlefield intelligence used for tactical decision making. So uh, uh, besides that, industry, the it in manufacturing or assembly line, computer vision is being used for automated inspection, identifying defective product on the production line, and remote in of ministry. The technology is also used to increase the efficiency of the production line. Automotive. This is one of the best example of computer vision technology, which is the dream come true for human. Self-driving AI analyze data from a camera mounted on the vehicles to automate lane finding, detect obstacles, and recognizing traffic signs and signals. So automated leaf reading. This is one of the practical implementation of computer vision to help people with disability, though who cannot speak. So it reads the movement of the leaves. What to tells, it read from their leaves and compare it to the already known movement that were recorded and used to create the model. So leaf reading also another important application of computer vision. So although there are uh, uh, many of applications, so these are some application. 10 application uh, uh, we have discussed here. So if you get a question, what is the application in computer vision, you may write this test point or any other application also. Fundamentals of image formation. How does the image form? Okay, so uh, when we take an image, you know that suppose you are using your mobile phone to capture an image. You know that the size of image is too large as compared to your computer screen, your mobile screen. So how it is captured by a camera and stored in your mobile? How it is viewed in your screen? The size of the image is physical size. If you compare your physical size of an image and physical size of a screen, your computer screen or your mobile screen, which is too small. And besides that, an image is a 3D object. It has some width, length, and also some height. But your screen is a 2D. So you see here, image formation is an analog to digital conversion of an image with the help of a 2D sampling and quantization technique that is done by the capturing device like camera. So in general, we see a 2D view of the 3D world. That is why it is a 2D view of the 3D world. So uh, image, it is analog to digital conversion because a image is a object is in analog form. But when you take the capture in an image, so it is converted to in digital form. In the same way, the formation of analog image took place. It is basically the conversion of a 3D world that is our analog image, to a 2D world, that is our digital image. So our analog image is 3D, where basically the digital image is 2D. We have already discussed. A frame grabber or a digitizer is used for sampling and quantization the analog signal. The making of 3D world object into 2D digital image plane is known as imaging. So the term imaging is nothing but it is only a mapping of a 3D world object to a 2D digital image plane. Because the analog image is the 3D, but our screen is a 2D, digital image is 2D. So there should be a mapping from a 3D to 2D. So this process is known as imaging. In order to do so, each point on the 3D object must be correspond to the image plane. Optical system. The lens and mirror are crucial for focusing the light coming from a 3D scene to produce the image on the image plane. So there should be a lens and mirror. This system define how light is collected and where it is directed, and consequently affect the sharpness and quality of the image produced. Uh, the goal of image sensor like CCD or CMOS sensor are to simplify, transform the optical image into electrical signal. These sensors differ by sensitivity, the resolution that they deliver affecting the image as a whole. So image sensor also there, optical sensor there. Then resolution and sampling. We know that the resolution is defined as the sharpness of an image, and it occurs technically as the number of pixel an image can hold. The number of pixel an image can hold. The number of pixel is a particular unit area. You the resolution you know. So sampling is the art of taking samples or discretizing the digital signal and representing a continuous analog signal as a grouping of discrete values. It can be seen that high resolution and appropriate sampling rates are required in order to provide detailed and accurate image. So high resolution is required, and a good sampling rate is also required to produce a good quality image. Image processing can be described as the act of modifying and enhancing digital image by using algorithms. So we know that image processing is nothing but it is a process by using some algorithm, by using some techniques, how to process the image to get a enhanced image, to get a better quality image. Pre-processing includes activities like filtering, noise reduction, and color correction that enhance image quality and information extraction. The second component, the next component is color and pixelation. In digital imaging, a frame grabber is placed at the image plane, which is like a sensor. It aims to focus the light on it, and the continuous image is pixelated via the reflected light by the 3D object. The light that focus on the sensor generate the electrical signal, and each pixel that is formed may be colored or gray depending upon the intensity of sampling and quantization of the light. So each pixel depend upon gets its color by depending upon the intensity, which is using sampling and quantization of the light that reflected and electronic signal that is generated via them. All the pixel from a digital image, the density of these pixels determine the image quality. So the more the density, the more the clear and high resolution image we will get. So if the number of pixel is a unit area is more, so you will get a enhanced picture, better quality picture. So we have already discussed there's the ideal size of pixel should be there to get a better quality picture. Okay, so the number of pixels present in an image determine its quality. If the number of pixels is more, it is a good quality picture. Otherwise, it is a poor quality picture. Okay, so we know that for making a digital image, we have performed two sampling and quantization. In the very first class, we have discussed that there are two techniques used for those purposes. One is sampling, another is quantization. Sampling is a spatial resolution of digital image, and the rate of sampling determine the quality and digital image. The magnitude of the sample image is determined as a value of the image processing. It is related to the coordinate values of the image. So as you know, the sampling is associated with the location of the pixel x, y, and quantization is associated with the frequency or gray level value of that image f of x, y. So quantization is the number of gray level in the digital image. The transition of the continuous values from the image function to its digital equivalent is called quantization. This is related to the intensity value of the image. So we know that the sampling is associated with the coordinate value, location value, and the quantization associated with the intensity value. The normal human beings acquires a high level of quantization level to get the fine shading detail of the image. The more quantization level will result in the more clear image. So it is required improve accuracy. So digital image is less susceptible to the human factors and gives accurate output of the object with high details capture. So it has a improved accuracy, enhanced flexibility. So unlike your analog image, digital image are easy to manipulate, edited or analyzed as per the requirement through different software. Hence, they provide flexibility and post processing. So the digital image is more flexible for different software. The software used to manipulate it, edited it, and also applying different processing technique. So that is why the digital image is suitable for this purpose. High storage capacity. Data in any digital format, such as in one or more digital image, can still be stored in large amount while very high resolution quality. So the storage capacity, the storage amount will be less. Easy sharing and distribution. The use of digital image allow them to quickly duplicated or transmitted across various channel and to various gadgets. So the digital image is easily transmittable. You can send digital image easily. Advanced analysis and capability. Digital imaging enable the application of analytical tools including image recognition, machine learning, which can provide better insight and increase productivity. So digital, that is why we need to transform or convert the analog to digital one. Beside this, it suffers some drawbacks, some disadvantages. Data size. Large structured digital image could occupy large storage space if the large structured data and computational power hence may be expensive in this application. So in this scenario, this is also a drawback, data size. Image noise. Digital image may be compromised by noise and artifacts which degraded the image quality, mainly when photographed at night or using low image sensor. So when photograph it contains some image noise, so the quality may degraded. Dependence on technology, yes. Digital imaging entails the use of sophisticated technology and equipment that may be costly or there may be constant need to service or replace equipment. that is, it always depend upon the technology. Privacy concern. The ability to take and circulate the photograph digitally also process concern because personal information can be photographed without the subject permission. So there are also some privacy concerns. Data loss risk also. That is some issue in security. Digital image repositories, however, are prone to data loss caused by hardware failures, corrupting software, or unintentional erasure. So these are some disadvantages, although it has many advantages. It suffers this type of drawbacks. So these are some applications. You know that medical image, MRI, CT scans, surveillance and security, digital camera and imaging systems are greatly needed for various security or surveillance process. Are they offer live feed and also useful in acquiring data for investigations. Remote sensing. Digital imaging plays an important role in remote sensing application in terms of monitoring and mapping of environment. Entertainment and media. The entertainment industry involves the use of digital imaging in films, video games, and virtual reality to deliver improved visual impact. Scientific research also. Digital imaging helps in scientific studies through providing best picture at research fields like astronomy, biology, and material science. Then, introduction to object detection using image processing. So, the machine how does the machine detect the object? This is what type of object are there. Object detection is a crucial task in computer vision that involves identifying and locating object within an image or video. This task is fundamental for various applications including autonomous driving, video surveillance, and medical imaging. So this article delves into the technique into methodologies using object detection focus on image processing approaches. So the object detection is important because suppose on medical image, the doctor is interested to find the cancer cells in a patient's body. So for that image, it will detect that the machine will detect that this part is the cancer cells. So how does the computer uh, detect it? Key concept of object detection. Object localization. It involves determining the location of the object within the image by drawing boundaries boxes around them. So you may see in MRI report or CT scan report that this is the location of the your suppose there is a stone in a patient's body. So this is the stones. This is the location of stones, and more importantly, this is the dimension of the stone. Okay, so it is calculate the dimension. Um, this involves determining the location of objects within an image by drawing boundaries boxes around them. You may have seen that is there is a uh, rectangular box like rectangular box is drawn in a face. Recognize that these are the faces. Object classification. This involves identifying the category to which the detected object belongs. These are rectangular boxes used to define the location of object within an image. You see, this an image contain different type of object. Some human beings are there, some person are there, some object are there, some cup is there, laptop is there, keyboard is there, and some papers or books are there. You see, some rectangular boxes are drawn to recognize them. These are the books. You see, these are the person 0.78 person. So different other different person are there. It is recognize the cup. You see, you recognize the cell phone. You recognize the chair, tables, cup, laptop, book. So using a powerful object detector, so you detect the object. So this image contain different type of object. So yeah, object detector is there to detect that. And you see it draws a rectangular boxes to detect or recognize the object. So image recognition is the task of identifying object of interest within an image and recognizing which category the image belongs to. Uh, we have seen that in that picture that is it is categorized the different type of image it belongs. When we visually see an object or scene, we automatically identify object as different instances and associate them with individual definitions. However, visual recognition is a highly complex task for machines to perform, requiring significant processing power. So, image recognition work is a long-standing research problem in the computer vision field. While different methods to imitate human vision involved, the common goal of image recognition is the classification of detected objects into different categories, determining the category to which an image belongs. And therefore, we also refer to as deep learning object recognition. In past year, machine learning is particular deep learning technology has achieved big success in many computer vision and image understanding tasks. Hence, deep learning image recognition method achieve the best result in terms of performance, frame per second, FPS, and flexibility. We have already seen this is a powerful object detector used to detect the object. Different objects are in the picture, cup are there, cell phone is there, chair is there, person themselves are there, and one laptop is there, keyboard is also there, book, papers are also there. So it is recognize different object in an image. So there are some term image recognition and object localization. Object localization is another subset of computer vision often confused with image recognition. Object localization refers to identifying the location of one or more object in an image and drawing a bounding box around their perimeter. However, object localization does not include the classification of detected object. So it does not include any classification of detected object, but object localization refers to the identifying location of the one or more object in an image and drawing the boundary of box around their perimeter. Wording identified, but it does not include any classification of detected object. So it does not include any classification. You see, this is a face detection. There is an image, it contains some humans are there, but uh, uh, the human is detected, and by drawing some a green rectangular line over the web, so it is assumed that the each rectangle contain a face. This is a fake face recognition system. The term image recognition and image detection. The term image recognition and image detection are often used in place of each other. However, there are important technical difference. Image detection is the task of taking an image as input and finding various objects within it. So taking an image as input with finding an example is face detection, where algorithm aim to find face pattern in image. When we strictly deal with detection, we don't care whether the detection object are significant in any way. But the goal of image detection is only to distinguish one object from another, to determine how many distinct entries are present within that object. Thus, boundary boxes are drawn around each separate object. So, on the other hand, image recognition is the task of identifying the object of interest within an image and recognizing which category or classify they belongs to. So, these terms are different in this way. You see here, this is all are the vehicles. So, the real-time video recognition. So, car is there. One truck, you see. So, using a video recognizer, so you can detect the objects. How does AI image recognition? So, we will please write your name. We'll discuss about the how does the AI image recognition work in the next class. So please write your name and registration number in the board. Please wait 1 minute. I will give the attendance, take the snapshot.